This is brought to you by Southern Farming Systems through support from Glenelg Hopkins Catchment Management Funding through funding from the Australian Government's National Landcare program. SFS has support to run these types of workshops with the local community groups within the Glenelg Hopkins Catchment Management area. And we have the opportunity of running 3 of these types of workshops, with SFS having expertise in the fields of pastures, crops and soils. So if any Landcare groups or community groups are interested in running more of these types of workshops, whether they will eventually be face-to-face again or whether they will be online, look out for expressions of interest opening after the 30th of June 2020. So I'm going to now hand over to Cam Nicholson to discuss sodic soils. So you there, Cam?
Yes, morning Michelle, and good morning everybody. I'll jump straight into it, and I'm happy to take questions at any time. So either if you put them in the chat room, Michelle will then interrupt at the time that suits if I don't pick them up, or just unmute yourself and ask a question if anything's unclear. I do have a couple of spots during the presentation where I'll pause for any questions, but if you've got something on a slide I'm showing, then feel free to jump in. I want to start by just putting the whole idea of sodic soils into context. This is a map of Victoria, and as you can see, the colours, both the yellow, the pink and the green, are sodic soils throughout Victoria, and they can be acidic and sodic, they can be alkaline and sodic, or they can be neutral and sodic. So soil acidity doesn't have anything to do or in relation to the sodicity of the soils. But as you can see, there's a very large part of Victoria that does have sodic soils that we need to deal with. And Victoria's not alone. If you look at that from an Australian perspective, the red dots are where soda soils, or those sodic type soils, appear across the country. And as you can see, every state and every territory's got them. So they're pretty widespread across the landscape. And importantly, I want to, when we're talking about sodic soils, we do need a bit of an understanding of soil texture. So I just want to make sure we're on the same page with that and understand the sort of terms that I'll be using. So soil texture is simply the proportion of sand, silt and clay that's in a soil. So those 3 elements, sand, silt and clay, are really provide the definition of what a soil texture is. The diagram on the right just shows the size of that sand, silt and clay. So clay particles, which are the really small dots that I've got there, can be up to 1,000 times smaller than what a sand particle will be, and 100 times smaller than what a silt particle will be. The importance of that, of different sizes, is the way they arrange themselves. Importantly, if we're talking about sodic soils work on the clay fraction. So when I'm talking about changing things with sodic soils and using things like gypsum, we're really referring to the amount of clay that's in that soil. And they're very small particles that we're talking about. Some people also may have seen this triangle before. This is just a triangle that gives you that classification. So if you get a soil test or someone describes a soil as a loam or a clay loam or a silty clay or whatever it might be, they're simply referring to the proportions of sand, silt and clay that's in that soil. And I'll come back to this triangle, so I won't explain it now. I'll come back to it when I show you some results and why we did or didn't get a response to gypsum. And it will relate back to the soil texture and the amount of clay that we've got in that soil. To fractionate these or break these up into their individual components is a fairly costly job to do. So in the laboratory, if you get a test back from a laboratory and it says that you've got a clay loam or whatever else, the analysis is usually done simply by a test called ribboning. And so the little diagram on the right hand side here is how in the laboratory they would ribbon a soil out. And it's simply just getting that soil damp or wet, almost into a putty type consistency, and then pushing it through your forefinger and your thumb to see how far that soil will ribbon, or you can sort of stretch that out before it'll break. the more clay in it, the more it will stretch. You can imagine trying to do that with a sand, and there's no way you can do it. So the description of the texture of that soil is usually based in a laboratory based on a physical test rather than breaking it up into the three components. How those sand, silt and clay particles clump together or stick together is what we call soil structure. And the importance of this diagram is that you can see, because of the different size particles, when sand particles stick together, there are quite large gaps between those particles that clay and silt can fit between. And again, with silt particles, there are gaps there that clay particles can fit between if they're as individual particles. And that's really important because it determines how well air, water and roots can penetrate through that soil, because they can find gaps or cracks or pathways for that, that water, air or roots to be able to move. Now, importantly, the binding of these different particles together in that structure is created both by physical and chemical binding, or physical and chemical bonds. And it's important when we talk about sodic soils not to forget the physical type binding when we get caught up in all the chemistry about amount of sodium to calcium and so on. So I just want to touch on a couple of slides around the physical side of it first. So in the physical binding of the soil particles, I'm going to show you two pictures. This first one is a picture through a electron microscope, so you'd never be able to see this with your eyes. But they're clay and silt particles, are those tiny little blobs that look there like little lumps of soil, and that netting on it is fungal hyphae. So they come from funguses that you have in the soil. Very, very fine, can't see them with the naked eye. But as you can probably pick up from that, they can create a net-like structure that actually holds those particles in place. So it's a bit like putting a netting around a whole lot of loose bits of material, and they can potentially hold them in place. The other physical bonding that's super important is this stuff here. It's not green in your soil. It's been stained like this so we can pick it up. But it's a product called glomalin, and it's a glycoprotein. It's actually a sticky, gluey-like substance that comes out of the roots of plants when they grow, and also from funguses when they grow as well. So as those funguses not only create that root-like, that net-like structure, they also exude these sticky materials that potentially can glue particles together. And it's just a physical bonding of those individual particles to create certain types of soil structures. And both of those are really important in the formation of structure in the soil. If we move on now to the chemical binding of the soil particles, which is where a lot of the interest or focus is in using gypsum and dealing with sodic soils, I just need to go through a few basics behind that to start with. The chemical binding is created through things called cations, and cations are simply elements that have a positive electrical charge on them, and they're attracted to negatively charged particles. And both clay and organic matter have negatively charged particles on them. So if you can imagine, it's a bit like a magnet being attracted to a bit of steel. That one of them's positive, one of them's negative, and depending on how strong that magnet is, depends on how strong that bond is. But I just like to think of these cations that we're talking about as being just like magnets that can stick to the clay, which is like a bit of steel, or organic matter in this case. So both of those are important, but we'll focus on the clay for this discussion.
Just hang on there, Cam. I have a question.
Yes.
Does deep ripping sodic soils destroy the fungal hyphae?
Yes, is a simple answer to that. Any type of cultivation that disturbs the soil and physically breaks those physical bonds that you've created will cause the soil structure to decline. Now, obviously, cultivation in the topsoil would make that decline more than what a single rip might do in a subsoil. But just remembering, in the subsoil, if it's been pretty hostile and roots haven't grown there and funguses haven't grown there, you probably don't have many physical bonds anyway. the bottom line is that if you physically disturb a soil, you will break those bonds. You'll tear that netting and you'll break those gluey structures that have been created. All right, I'll move on. Now, the common cations we have in the soil, and you've probably heard about these: calcium, magnesium, potassium, sodium, and I've put aluminium in there as well. They're the common cations that we test for in a soil test in the laboratory, but secondly are common ones for that are present in reasonable quantities in the soil as well. So that's why I've called them the common cations. So these are these positive charged particles that are attracted to clay particles if you've got them in the soil. Importantly, they have different binding strengths. I've called their relative flocculating power. But basically, this is the strength of the magnet. And relative to sodium, if you give sodium a score of 1, calcium's 43 times stronger at flocculating or binding those clay particles together as a glue, if you like, as a magnet or a glue, than what sodium is. Magnesium's 27 times stronger, and potassium's only 1.7 times stronger than sodium. So if we want to stick those individual clay particles together in a way that is favourable to plant growth, roots and water and things like that, we want a lot of strong binding in that soil, which basically means we'd want a higher proportion of calcium, if we can, to the sodium that we've got. I'll show this again in a diagram form rather than in words. And so if people can imagine, these two little brown ovals that I've got there are two individual clay particles. And on those clay particles, they have exchange sites. So these are the magnets that are, if you like, on the clay particles. And different soils will have different numbers of these depending on the type of clay that it is. So their number of X's that they might have on that soil will be greater or less depending on the parent material of that clay. But if you can imagine, they've got these attractive sites on them. And then within the soil, what we have swimming around are things like the calcium cations, we have the sodium cations, potassium cations represented by K, and magnesium cations as well. And if you can imagine, in between two of those sites like that, you have these different cations, and they're gluing together those two clay particles. When the soil gets wet, so when water's added to a soil, what the water does is it drains through and tries to find these little gaps between the individual particles, is that water will push through between these individual, try and push through these, between these individual clay particles. If the binding of these, so the combination of those different strength magnets, if you like, or binding powers of those different cations that we've got there, isn't strong enough, the water will push between those two and separate those individual particles. So instead of being clumped together, they just act as individual clay particles. And so those particles float apart. And what you'll commonly see is this type of effect. So this is a topsoil effect. I know this paddock quite well. This is one of ours at home that was cultivated to level it off, and then it was sown and it didn't have gypsum on it. And you can see that milky sort of cloudy water once the rain occurred. That cloudiness is individual clay particles, so these individual brown discs there, just floating around independently of each other. And because they're so fine or so small that you can't see them with the naked eye, they just look like cloudy water. And when it dries out, you get the effect like I've got there on the bottom right-hand corner. So you get that crusting sort of surface effect on the top there, which can create problems when it's dry, and then it looks like that when it's wet. And that's called dispersion. So commonly used term is sodic soils disperse, and they disperse because those individual clay particles are falling apart or breaking apart. If we go back to our original diagram, and in the example before, we didn't have enough strength in the combination of the calcium. So while we had two calciums, which are really good and really strong, we also had a couple of lousy ones in there because we had some magnesium. We had quite a bit of sodium in there as well. So on balance, when you added all those up, the strength of those in combination wasn't enough to stop that water pushing those particles apart. So how do we change the balance on that? The quickest way of doing that is adding gypsum. And gypsum's calcium sulfate, as people will know, and the calcium sulfate, when it's applied to the soil and then water hits it, it dissolves into its calcium and its sulfate. So effectively what you're doing by putting gypsum on is you're flooding the soil with lots of CAs or lots of calciums. So you change the balance of those different cations in the soil, and that's what the gypsum's doing. And so when you add it there, you flood the soil with this calcium, as I said, and that can push off some of those weaker cations. So the ones that don't bond as strongly, they get pushed off by the calcium and they go off in different directions. Okay, so it doesn't completely eliminate all of them, but it pushes a lot of them off, and particularly some of the weaker ones that we've got there. So then we have these individual ones floating around in the soil. And I'll talk briefly at the end, but an important thing of getting a good response to gypsum in sodic soils is actually being able to remove this or leach this out of the area that we're trying to modify. If those particles can't be leached or washed away from there, the effect of the gypsum can either be short-term or reversible. Okay, and this effect of putting more of those stronger binders into that soil and clumping that clay together is what we call flocculation. And so it works and works fairly rapidly. So you can go from cloudy water to clear water as those individual clay particles clump together very rapidly. And I've seen it happen within a 24-hour period. Now, if we're able to measure the number of these X's that we've got in the soil, we can determine what's called the cation exchange capacity. So if you can imagine these blue X's that we've got on here are our exchange sites. The term we refer to is cation exchange capacity. All it's doing is simply estimating or calculating the number of these blue X's that we've got on those clay particles. Okay, and that helps us determine what the cation exchange capacity is.
Cam, we've got a question here.
Yes.
What effect does lime have?
Yep. Okay, I was hanging on to that towards the end, but I can answer it pretty quickly now. Lime is calcium carbonate, so they both have calcium in them, and theoretically they have exactly the same effect. The difference is how easily the two products dissolve. So to dissolve a ton of good gypsum, good quality gypsum, takes 50 millimetres of water or 50 millimetres of rainfall to dissolve a ton of gypsum if you put it out. To dissolve a ton of lime takes 4,000 millimetres or 4,000 or 4 metres of rainfall to dissolve the same amount of calcium out of it. So the difference in the choice between the two is really how quickly that can occur. You could be waiting many, many, many years, and that's why lime, if not incorporated, moves very slowly into the soil. Because it's just not soluble in water where gypsum is. And I've seen effects of gypsum working within, as I've said, if you put a sodic soil and you've got that cloudiness and you mix up some gypsum in water and you put it in there, you can come back 24, 40 hours, 48 hours later and that water's cleared. So it's a very rapid response compared to gypsum, which would take years and years, compared to lime that would take years and years and years. Right, hopefully it's answered that one. Just moving on to how to actually calculate the cation exchange capacity. And I'll talk about this in simple terms. It's a little bit more complex than this in the lab, but in a nutshell, what they do is they take your soil when it's in the lab and they wash it to displace the calcium, magnesium, sodium, potassium and aluminium cations off those X's. So if you can imagine that soil there, we put a chemical in it and it pushes all of those off. So there's none of those 5 elements are hanging on to the cation exchange sites. The quantity of each of those cations that we wash off is then measured, so we can measure the quantity of them. And if you add all of the cations together, that's how we determine our cation exchange capacity. So the assumption is that all of the cation exchange sites on your soil have one of these 5 cations stuck on them when you send it into the laboratory. And so once we've got those numbers, we can then work out various ratios and percentages. So when you hear about terms like exchangeable sodium percentage or calcium magnesium ratios and things like that, they're all determined once we've been able to do these 3 steps at the top. And so here's one I just grabbed, a very quick soil test that I grabbed for you. So in this one here, we've got the 5 different cations, and they're called exchangeable cations. And so what we've done is wash off the calcium and measured how much we've got, the magnesium, the sodium, potassium, and the aluminium. If you add those 5 numbers together, you'll get 5.15. So when you see this sum of cations or CEC, it's just the adding up of those 5 above. A common term that we use is the sodium percentage, or ESP, and I'll refer to that a bit later on. The ESP in this soil is 5.2%, and that is simply how much sodium have we got. So if you took 0.27, this number here, divided it by 5.15 and turned it into a percentage, it would be 5.2%. Same with the aluminium, 0.72 divided by 5.15 gives you 14% aluminium as a percentage of the cations. And the calcium magnesium ratio is just how much calcium we've got the magnesium. So it's really 2.24 divided by 1.16. That's how you get the 1.4 there. Okay, so the numbers that we talk about of percentages and ratios are all determined by these 5 numbers up here. And the total gives us an insight to how much cation exchange capacity that soil has got. And if we're flooding calcium in it, we're flooding it to try and change this balance here on those total cation exchange sites that we've got. Now, in sodic soils, one of the ratios that we focus on a lot, and there's been quite a bit of work done with it, but the rough rule of thumb is that if we have a sodium percentage of the cations, or ESP, exchangeable sodium percentage that refers to, less than 6, then soils will flocculate. Clay particles will flocculate in the soil. If the exchangeable sodium percentage is above 6, then those soils will disperse and float around as those individual particles. So it's a very commonly used number to determine, are these soils dispersive or likely to flocculate or structure together. And here's the first of my 2 red warnings as I go through this. Don't rely just on the chemical test results to decide on the use of gypsum. I've seen many cases, and I'll give you some examples of some recent trial work we've just done, where while the chemically it looks out of balance, in other words, the exchangeable sodium percentage is above 6, the physical bonding of that soil is enough to override or overcome or prevent the chemical imbalance causing dispersion. So just because chemically it's out of balance does not necessarily mean that it will disperse. Okay, really important point. And I would never use gypsum, particularly given the cost of it with transport and also sourcing it now, if I didn't know that the physical bonds were broken as well.
Cam, I've just got a question here. Why have some tests with hydrogen percentages reported? Why do some tests do that and not others? And what impact does the hydrogen have?
Yes, yeah, really good question. Hydrogen does have some effect. So, and I've skipped over this, but pH does have an influence, and pH is, the P stands for potential, the H stands for hydrogen. So when we talk about acidity in soil, we're actually talking about hydrogen ions, or that H+ in there as well. Some of the newer tests that are being developed also include hydrogen in them as well, because then it can take into account the pH of the soil. Our original starting point with this didn't include hydrogen in it. I think certainly in sodic soils that are acidic, then the amount of hydrogen should be considered as part of our calculation. So remember that first slide I showed where we had alkaline soils, neutral soils and acidic soils? It was just at that time the hydrogen was excluded. Now it's only really relevant, changes the thinking around this, if we're in acidic sodic soils. But there are quite large parts of certainly southwest Victoria that are acidic sodic soils, and that would come in as a should come in as another calculation. And if it does have a important influence. If I go back to these numbers here, and if I put hydrogen in here as well, and say it's acidic, so there's quite a bit of hydrogen floating around, that sum of the cation number becomes bigger. So let's say there's 0.85 exchangeable milliequivalents, 100 grams of hydrogen in there, so that number becomes 6. If you then divide 0.27 by 6, the sodium percentage isn't 5.2%, it'll be smaller. So it has an influence on acidic soils, and in fact on acidic soils this estimate of sodium percentage usually overestimates or will trigger thinking that this soil is dispersive when in fact it's not. Hopefully that's answered it, Michelle.
Yeah, thanks, Cam.
All right, I'll move on. So what's the test that simply we can do to understand the physical strength of that bonding in the soil? Because the stuff we get from our soil test really is giving us that chemical balance bit. Okay, some people may have heard of this. It's called a dispersion test, really simple to do at home. Select 2 to 3 small aggregates about the size of a pea I talk to people about. So if you get your soil, break it up and have little chunks that are about the size of a pea. 2 or 3 of those in a container. Place, so I've got 75 ml of distilled water. This is the protocol, but some water in that container, but make sure that it's distilled water, water that's come out of a plastic tank or water that you collect in a bucket once it's rained. Don't use water out of things like concrete tanks because they can potentially leach ions into them, so you'll get calcium and things like that in them, which will, in a sense, act like gypsum anyway, so you'll get a false reading. So distilled water, and don't disturb it for a period of time. So that's what I've done there. That's just been set up, 2 lumps of soil in there, and then some distilled water in there, or iron-free water in there. Okay. Then you check it after 2 hours and after 20 hours. They're the standard sort of times when they get checked. And we're looking for cloudiness, the colour of milky tea. So it's a pretty strong milky tea, but you can see there how the water around it has gone from that one there that was clear to something where that's really quite milky around it. So they're the individual clay particles falling apart as water moves between them. And it's a really simple test that we can do. If after 2 hours and 24 hours that we don't get any dispersion, then you grab some more soil, put it in some sort of a bowl or a bit of a container, and add sufficient water to bring that to a soft consistency, a bit like a putty sort of consistency. So you're adding water with a spatula, mixing it around till it gets that putty-like consistence, okay? And you're mixing that round a bit. And then without using your fingers, just form a cube or something again about the size of that sort of pea size, and then repeat that same process, but this time with that reformed bit of soil rather than the original soil that you started with. And don't stir it or disturb it, and then check it again after 2 hours and 20 hours. And that's what's called a remold test in the jargon, or in the protocol for the test. And what that is aiming to simulate is if we'd cultivated and broken those physical bonds on the soil, that's what your mixing with the spatula does with the water, is breaking those bonds and then seeing if it disperses again. And given the cost of gypsum, I would do that every time, irrespective of what the chemical ESP ratio is or ESP percentage is. Have we got another question there, Michelle?
It's just asking about, is there a possibility to get a copy of the slides? We will be sending out a copy of the slides and a recording of the webinar post-webinar.
Yes, yes. And this dispersion test that I've got, if you do the proper, it's called an Emerson dispersion test, they do have more steps and more sort of fine detail to it. You can actually request this on a soil test. You've got to pay extra money for it, but the laboratories will do it. So they will do, first of all, a dispersion test, and then if you tick the right box, they will also do what's called the remold test, and they will give you that information as well. And really, for an extra, I don't know, might be 40 or 50 bucks or something, if you don't want to do it yourself, it's worthwhile doing. But having said that, it isn't that hard to do, and gives you, I think, some really useful information. And I'll just show you how that can become very important. And I want to show you some results. I do some work with a group called the Woady Yaloak Catchment Group, just south of Ballarat, around sort of between Cressy and Ballarat. And this was a site where we did some gypsum trials just at Berrybank. And I'll just show you these results very quickly, but you'll see how the idea of a physical dispersion test becomes important in the whole thing. So gypsum trial, this was a paddock. The work was done in conjunction with Precision Ag, and I know that Ben and Kirsten are on the line here. So this project was run in partnership with them, where the paddocks were mapped using grid sampling. We also did some deeper strategic sampling and also did some EM sampling on them as well. I've just pulled out one site here, which is fairly even. It's a 25-acre paddock down, as I said, at Berrybank. The numbers there, so 11.4 that I'm circling there, 12.6 refers to the exchangeable sodium percentage in the topsoil, top 10 centimetres from the laboratory. So this was picked up, so through the grid sampling we were able to identify where those different sections were in the paddock, and as you can see, this one's fairly even, and you would say on balance that this had exchangeable sodium percentage above 6, so therefore a really strong candidate for dispersion. So we ran a trial where we put a strip of gypsum in one part of the paddock and no gypsum in the other, and then compared the yield through a yield monitor. So this was a canola paddock and was very good canola crop. So on the right-hand side here is where no gypsum's been applied in a strip there, compared to 2.5 tonne of gypsum across the rest of the paddock. And if you look at them, there's no outstanding difference. You would have thought if the 2.5 tonne made a big difference, a lot of these areas here, particularly along the border, you may have seen a difference to the response to gypsum. But we didn't see that. The yields came in there at around about 3.6 tonne off both the no gypsum and the gypsum as well. So no significant difference in the yield between those two paddocks. Despite what you might think if you just look solely at the results of the soil test here, that the exchangeable sodium percentage was above 6. So when you start thinking what might have caused that, first thing is, and I mentioned this at the start, when we're talking about calcium and we're talking about dispersion and flocculation, it acts on the clay particles in the soil. Because we did detailed soil testing here and soil analysis, we could work out accurately what the proportion of sand, silt and clay was. So that's the top 10 centimetres, 10 to 20, 20 to 30. The blue represents the amount of sand in the soil, the orange the amount of silt, and the grey the amount of clay. And as you can see in that topsoil, even though we thought, oh, this will be a soil that will respond to gypsum because of the exchangeable sodium percentage, we were only dealing with about 25% max, 20-odd% clay in that soil. Did get heavier as you went down, so we did get more clay as you went down in depth. If I come back to this triangle now, and if I map those three portions on this triangle here, the first one, it's got about, so we start off with the amount of sand that we've got, so we read along the bottom here until we get about, in this case, it was about 45% sand. So we draw a line up there. We then look at how much silt we've got. And so this is the silt running down here, and we've got about 30% silt. That represents about 30% silt. So you draw a line down there. And then the bit of clay that we've got, 20-odd% clay that we've got. And where those three intersect is where we get the description of that type of soil. So it intersects there. So effectively, we were putting gypsum and doing all of this on a loam soil. And from my experience, if we're dealing with loam soils, rarely is dispersion likely to occur because we simply don't have enough clay to be working with in the scheme of the whole soil that we're dealing with. So loam soils are pretty rare to actually get some large-scale dispersion occurring on them. Doesn't mean it can't happen, but they're less common. The other thing is we did a physical dispersion test on them, and the 4 containers on the left-hand side come from the no gypsum strip, and the 4 containers on the left-hand side from the no gypsum strip. The 4 containers on the right-hand side come from the 2.5 ton strip. So this is when we started. So we've got those couple of cubes there. This is 2 hours, and you can see that both the gypsum and the non-gypsum site, we've seen no difference in the cloudiness of that water, and no difference in the cloudiness after 20 hours as well. So that's telling me that even in the no gypsum site here, those physical bonds that are on that soil that have been created over time are holding that together, even though the exchangeable sodium percentage is out of whack, or would give you the indication or the suggestion that that soil will be dispersive. When I've done the remold test, and that's the remold test there is some degree of cloudiness, but not a hell of a lot, and less so in where the gypsum's been applied compared to where the no gypsum's been applied. And that's largely a function of not having a lot of clay in that soil in the first place. So as we get more clay in it, which is coming up this way, so clay loams and clays and things like that are more likely to be responsive than those lighter soils. So the message I'm trying to stress to you is that it's not just, don't just look at the exchangeable sodium percentage and think, gee, that's high, it needs gypsum. Do some other investigations to make sure you're getting it right. Might pause there just for a tick, Michelle, and see if there are any questions. No, if not, the silence, I'm assuming everybody's either
yeah, I haven't got anything. Oh, hang on, Mark, you've got a question there?
Yeah, I was just going to ask Cam, so just going the other way, I guess, is if we didn't see higher sodium percentage, is there still the potential to see dispersion issues, I guess? If you know, if you know what I mean, like the opposite effect?
Yes, I do. Yes, I do. And it's a really good question because particularly when the hydrogen bit comes into it, there's a new test that's being developed by a scientist or a semi-retired scientist over in University of Adelaide. And instead of just using the exchangeable sodium percentage ratio, he has a different calculation that takes all of the cations into account, their binding power into account, and the hydrogen into account. And when you do that, and I've compared these in the trial that we did, I've compared those to the typical ESP test. In some cases where the ESP would be below 6 and you'd say you're not going to get a response to gypsum, in other words, that soil will be flocculated. If you use this new test, which has the hydrogen and the different binding strengths in the calculation, it would say that it is dispersive. So that might be a long-winded way, Mark, of saying that yes, it is possible to get soils that will disperse with an ESP below 6. And there is another test that is, well, hopefully available fairly soon, that's robust enough to be able to pick that up. But again, even if you're not doing exchangeable sodium percentages, then I would still be doing your dispersion test. And I should say that paddock that didn't disperse, when you talk to the farmer and what on the last 5 years, that's all been in no-till. So it's had 5 years of cropping with no-till on it, and then no grazing afterwards. So it hasn't had livestock on it either. So there's been, if you like, no physical disturbance of that soil apart from the sowing actions and where the tyres might have gone in that controlled traffic type approach. And that makes perfect sense to me after 5 years. If you're growing good crops on that, the funguses and the fine root hairs and those glues that are created from that glomalin will stick those soil particles together, particularly if you don't have a lot of clay that you're dealing with.
Yeah.
We've got a few coming in on the chat box there, Cam. So Rick's asked, So would it be inadvisable to work with that loamy soil?
Would it be inadvisable to work that loamy soil? Is that what
That's
was meant?
correct, yep.
Yeah, okay. Yeah, so just remember, if you work that loamy soil, you would have, so let me flick back to it, you would change that soil structure when it gets water on it from that to something that looked like that. Now, there's a bit of cloudiness. It's not as bad as a lot of examples I've seen, but there's a bit of cloudiness. Those individual clay particles have to go somewhere. So they're likely to go in between the silt and the sand particles, the bigger space in silt and sand particles, and potentially block those pores or those spaces up. So when you've got something like that, you're really on that borderline of do you put gypsum on or not? If that was in a pasture situation, so we're dealing with a lot of small seeds, I would probably think about putting gypsum on. If you had some more robust type plants that were growing, then potentially not. Because that's sort of right on the borderline for me of whether I'd get overly excited about using gypsum or not. Small seeds in pastures, I'd certainly see a difference. Wheat, barley, that sort of thing, probably not in that situation.
The other questions we have from Mark is, we have sodicity in the clay at deeper than 0 to 10% layer. Would you care to comment on gypsum in that area?
Yes. Can I hang on to that? Because I'll move on to those couple of slides now, because I reckon, to me, all I've really been talking about in these last few slides is about surface sodicity and the sort of effects it might have there. Subsurface, different story, and I'll relate a few stories from when I started 35 years ago in Kerang in the irrigation districts, which were highly sodic soils where we were exposing subsoils when we were laser grading for irrigation.
And I think that will fit in with Mike's questions of what are your recommendations with managing grazing in sodic soils as well.
Yeah, okay. Well, the grazing one's an interesting one. Because the grazing, you can sometimes get those physical breaking of bonds of the soil just because of hoof impact, because of grazing. So you almost have your little plough working there constantly whenever you're grazing. But the only time you get those really bad breaks in those physical bonds is when the soil is so wet that the soil loses its strength and can't support the animals walking on it. So you get pugging. So I've seen this in examples of pugging, particularly dairy cattle, when it gets too wet, and just the weight and the hoof impact pushing into the soil and pugging it is the equivalent of what that would be in the remold test. And so we can run into some serious strife because of that, because you're breaking those physical bonds. The flip side of that, a pasture, and generally a perennial type pasture, the fine root hairs on the grasses that you grow in particular tend to do a better job at binding than what some of our crops might be. So you imagine if you compared the type of root structure that canola's got to the root structure that a perennial ryegrass might have, then because you've got those different structures and things like subclover with very fine root hairs on them as well, they tend to create those physical bonds quicker than what your cropping rotation might do. But animals can still create that same plough type effect simply by grazing at times when the soil can pug. When it doesn't pug, the effect of it is much, much less. All right, I might move on, Michelle, just cautious of the time.
Yeah, no, that's answered everyone's questions to date, so we'll...
All right, a couple of 10 minutes just to finish off around a couple of things. One is around gypsum. So gypsum, as I mentioned before, is calcium sulfate. So it's calcium, it's sulfur, and it's got some water associated with it as well. And lime's calcium carbonate, as I mentioned before, and they're the two dissolving rates of those. Depends a little bit on the pH of the soil or the pH of the water, but just take those as ballpark figures. You know, so you're dealing with a hell of a lot more, about 80 times more water you need to dissolve a ton of lime than a ton of gypsum. So that's why we favour gypsum over lime, to try and get that quick effect of the calcium. Usually when you're applying lime because you want the carbonate, you want the CO3 to react with the hydrogen ions to soak up that hydrogen, which in turn reduces the pH, the potential hydrogen in the soil. So they perform two different functions. With lime, it's the carbonate that you want. If it's gypsum, it's the calcium that you're really trying to buy. And you see this, if we need a quick dose of sulfate, sulfur in the soil, then we'll put a dusting of gypsum on. And why it works instantly, because as soon as it gets wet, it dissolves and it's gone. Sources of gypsum, three sources, or two main ones now. One probably most people are familiar with, which is your natural or your pit gypsum. And it's just dug out of the ground, same as lime. It accumulates in shallow layers or pits, and it's a salt. And it's just an accumulation of a certain type of salt that has lots of calcium and lots of sulfur in it. Years ago, we used to be able to get byproduct gypsum, pretty hard to get now, called phosphor gypsum. And that's when we used to manufacture a lot of fertiliser from raw products in Australia, and that used to have a bit of phosphorus as well. And you'll see that bit of gypsum. If anybody's put single super out and you get your first little rain and you think your super hasn't dissolved or washed in yet, because you see those granular particles, those little white particles on the ground, that's actually a bit of gypsum that's left behind. The phosphorus will have been soluble. Phosphorus will move out of those particles, those gypsum particles, into the soil on a heavy dew. 1 or 2 millimetres is enough to wash them out. It's just a bit of gypsum that's left behind that takes a little bit longer to dissolve. Byproduct gypsum was one that we used to be able to get, can't do much of it. And some people might have seen rejected plasterboard. The challenge with the rejected plasterboard is that in the manufacturing process, it's common for them to use a glue that isn't all that water soluble. So you buy something that you think's water soluble, but it's stuck together by something that isn't water soluble. So the rate of reaction is much slower. The chemical concentration of it, of the calcium, can be similar, but it just doesn't dissolve as quickly because of the manufacturing process it's gone through. Now, if you buy pure gypsum, you're getting 23% calcium. So that's the maximum you get if you bought pure gypsum. In Victoria, believe it or not, there are laws to selling gypsum and how you can describe it, if it's called gypsum to start with, but also the grading of gypsum. And I've just listed there a grade 1 or highest quality gypsum in Victoria. When it's sold or being marketed, it's got to have a minimum of 80% gypsum in it or 19% calcium. So it can have other impurities, but it's got to have at least 80% calcium, grade 2 and grade 3, so on. So they're just lower qualities or purities. And importantly, lower in the amount of calcium that you're actually buying. And it's the calcium that we're wanting to buy to actually displace those other cations that we don't want.
We've got a couple of questions there, Cam. So does the leaching of the sulfate component of gypsum increase with pH? And at which point will the salts in gypsum impact soil biology?
Wow, they're two good questions. So the first one was, how does pH affect?
Sulfate component of gypsum, the leaching sulfate component.
The leaching sulfur. Okay, so sulfur's in the soil in two general forms. One is what's called elemental sulfur, and the other one's called sulfate sulfur. Sulfate sulfur is the form that plants suck or take that nutrient up. Now, importantly, sulfur can flick between the sulfate, the SO4 form, and the elemental sulfur form. So it can go from one form to the other, and tends to do that by being bound up in organic matter. So,
I've got the question wrong there apparently. No, does the leaching increase the pH?
Does the leaching of the sulfur increase the pH?
Yes.
Not that I increase the pH. No. So the sulfur, go back. If we talk about lime, it's the carbonate, the CO3, that reacts with the hydrogen ions that produces, in simple terms, carbon dioxide and water. Okay, so the reaction has to be hydrogen with the CO2, or CO3 in the carbonate that reacts together. Hydrogen doesn't react with the sulfur, so you don't get the mopping up of those hydrogen ions with the sulfate in it. Okay, it doesn't work the same way as the lime works. And the second question, Michelle?
Question, At which point will the salts in gypsum impact soil biology?
Yeah, don't know. Don't know. No, I'll leave that because otherwise I'll be uncertain of that. There's a huge amount about soil biology that we don't know. I don't really know what ratios or concentrations you start getting those effects. Someone else might, but sorry, it's not my wheelhouse.
Thanks, Cam.
All right, move on just to the last little bit. Sorry, I've got there, it should also contain gypsum less than 0.8% sodium chloride or salt. So we've got to be careful, particularly with the natural gypsums that you're buying, because they are essentially just a concentration of a salt. It was quite common that you get other salts with them as well, and sodium chloride is a classic one. And so a lot of the pits around northern Victoria, because they have fairly high water tables, and those water tables are saline, that you will also get, in a sense, contamination of sodium chloride. Remember, sodium chloride's got Na in it. Sodium is Na. So unless you're careful, you're buying gypsum, but you're also buying the problem as well. And so on the label, it should tell you what percentage of sodium chloride it is. And ideally less than 1%, 0.8% is what we should be looking for in the amount of sodium chloride. And that should be on the label or on the product disclosure when you buy it. And that is by law in Victoria. There is a Natural Gypsum Miners Association. That's their website there. I just went on, there's about 40 people or 40 miners associated with the Natural Gypsum Association. I went on their website yesterday afternoon just to check it, and my virus checker said that there was a virus on the website, so don't go there. So I'm putting that in as a disclosure. If you go there and click on it and you get something nasty on your computer, then don't blame me. But up until recently, they did have a website that worked, which was pretty helpful at identifying where all those different pits were, and could give you some information around the quality of the gypsum that was available. Just finally, how much gypsum do you put on? Now, when I started in Kerang, as I said, 35 years ago, it was pretty rough, the amount of gypsum that we were putting on, and sadly, gypsum and sodic soils have really been a poor cousin to the work we've done on lime and soil acidity. So this is my table of the rough rule of thumb that I use if I'm making recommendations to clients on how much to put on. So it takes into account your soil texture and your exchangeable sodium percentage. In very coarse terms, the more clay you get in there, the higher the cation exchange capacity. And in general terms, therefore, the more product you're going to need to put on to saturate those cation exchange sites with calcium. So it takes into account how much sodium we've got there that we've got to get rid of, and what that cation exchange capacity is. So if you had a clay soil and it had an exchangeable sodium percentage of 10, then you'd need 5 tonne of gypsum per hectare as a rough rule of thumb. Okay. There are more sophisticated calculations that are available in the literature. And this works on the basis of displacing the sodium with the calcium. So knowing how much sodium you've actually got there as far as the quantity goes, and saying I have to push that off and replace that with calcium, is a better way of doing that calculation. We'll share it in these notes, so I don't have to go through them in too much detail, except to say this table that I've got here, so this is for grade 1 gypsum. Remembering that you've got different qualities, so different purities of gypsum for different cation exchange capacities and exchangeable sodium levels. This is only in the 0 to 10% mark. So this is the cation exchange capacity down here from 10 to 20, and the exchangeable sodium percentage across there. Now the caveat on this, or what changes in these tables, is that also these calculations take into effect the bulk density of the soil, how efficiently sodium is pushed off by the calcium, and that will vary a bit, and how much of that sodium, once we displace it, we actually remove from the location, or move from that area. And I'll make a comment on that on my last slide, this idea about the leaching that has to occur as well to get the maximum benefit from the application of that gypsum. If we went through exactly the same as we did with my rough rule of thumb, We've got an exchangeable sodium percentage of 10, which we had on the last one. And let's say that clay soil we were dealing with had a cation exchange capacity of 14. Then using this method, we would put on 5.3 tonne, where my rough rule of thumb was about 5 tonne. So it's sort of in the ballpark. This does give you another degree of precision if you want to go down that path. But this does change or is influenced by these assumptions that we make down here around bulk density, efficiency of sodium displacement, and the percentage of leaching, which we don't have an enormous amount of understanding around for different soil types. We do have some, but it's not huge. And so my last slide and my second red warning, if gypsum's applied, then the effect relies on receiving enough water to leach the sodium and magnesium out of the root zone. So insufficient rain, layers in the soil that prevent downward drainage, and so sometimes we will have these heavier layers at depth that actually prevent drainage, and we know the bucket basically fills up and won't drain and we get really waterlogged, and or high water tables, which you see in northern Victoria, can reduce the effect of the applied gypsum. So if I go back to my irrigation example, because we only had a water table 2 metre, metre and a half from the surface, every time we'd flood irrigate, while we would be able to saturate that soil and move that calcium in, we didn't have anywhere to push the sodium that we pushed off that soil further down in the soil so that that soil could restructure. So we had this constant fight between the sodium pushing up from the bottom and trying to push it back down again through leaching. And so there are different effects that you get depending on how effectively we can get this downward drainage to occur. And so if we don't get enough rain, or we have these layers that prevent that, that can certainly have an effect on particularly trying to treat sodic subsoils. And I think it's one of the reasons why we struggle a heap of trying to get our sodic subsoils to change with the application of gypsum on the surface, is that we have this struggle with getting the right leaching to allow that to occur, which is a natural function. As you start getting more clay in the soil, you'll tend to find that some of those soils don't leach as effectively, particularly if they're sodic, because all the pores are blocked up to stop that drainage. So it's a real difficult one to deal with. And on that note, Michelle, I'll pull up, I think, and open her up for any final questions.